So this is the title of our presentation. As you see, we continue with the topic of fuzzy or F transform. Some preliminaries were given today in the morning at the plenary session, and I am happy that at least you have the basic idea how it works. However, in this talk, we will be focused on the application of this technique to numerical methods, and especially to numerical methods that solve integral equations. I'm trying to learn how it works. Jak se to připne? Okay. Now, thank you. So this in blurred, you see the table of the content. And actually, this is the motivation you can read, I will explain. The main idea is to use this technique for the numerical solution of integral or differential equations. And so here is the example of the integral equation which we will be focused on. And actually, I know also from my student time, I know that integral and differential equations do not belong to the topic which students love so much. However, after this presentation, I hope that you will love these equations actually, because I will explain you how easily and elegant you can find solutions of this type of equations. So this is an example of the equation which is called fractional integral Volterra. I'm trying here to use now. Okay, now I know how it works. So this is the integral fractional equation. Fractional means that this kernel is weakly singular. Weakly singular means that when parameters approach boundaries, then this term goes to infinity, and this makes the complication of first of all solution even regular, and especially for numerical solution, because the computation of terms that are very large actually causes also large errors, and therefore the main trick is how we can manage numerical computation when we solve this type of equation. Some details. So here you see that this is parametrical equation where the main parameter is beta. Beta is the fraction actually, and this beta belongs to the interval 0, 1, without boundaries. And the unknown function is y. So this is the equation that should be solved with respect to the unknown function y. And the complication is that this function y appears on both sides. Here it appears as itself, and here it appears as an integral term. So this means that the main trick is how we can apply any kind of numerical method to solve this equation. Then this equation, in short, can be represented using this operator form, where the operator I, B, stands for this integral operator, which is the most known fractional operator. And to convince you that really this type of equation is somehow basic for other examples, I show you other equations. They are known as initial value problem. Instead of integral form, they include differentials or forms of differentiation. And both of these forms, again, are fractional. So the first equation includes the Caputo fractional derivative, and the second includes the Riemann-Liouville fractional derivative. I will not go into the detail because today our main topic is how we can manage a solution of the integral equation. However, you see, if we can manage solution of the integral equation, we can also manage solution of these related differential equations. So in order to just prove what I said, here both equations are rewritten with the help of the same integral operator. So just to see that really that's the case. But as I said, we will be focused on the solution of the integral Voltaire equation, which I showed at the beginning. So after we formulate the problem, the next step is to understand whether this problem is solvable in principle, because we cannot imply anything when solution doesn't exist. And therefore, our first attempts are focused on the analysis of the so-called solution space. Luckily, this equation is solvable, and solution in the solution space is unique. However, in order to characterize this solution space, we should put some restrictions on involved functions, and restrictions are here. Again, I will not read. We will do it quicker. So the restrictions tells us about that the function should be bounded, and its first derivative should be bounded as well. However, this boundary is again a bit tricky, because here you see the same parameter is involved. And the solution is unique in this type of Banach space. This is complete functional space where the norm is given by this expression. So important to have Banach space means that the solution can be found as a sequence of approximations. Otherwise, the closeness of this space is not important. However, for this particular problem, we need closeness, and we need closeness with respect to this norm. It should be respected. Okay, so let's go. And as I said, so now we have problem, we have information that solution exists, and now our task is how we can find this solution. However, we will not find it analytically. I mean, I will not write you an analytical expression and say, so this is the solution. Because in most cases, the analytically expressed solution does not exist. Therefore, we shall find numerical methods in order to obtain approximate solutions. And now the role of F transform here is very important, because we will find the solution using this type of, again, linear transformation. So here I will explain you some details of our approach. First of all, we, sorry. I again pressed some, so we are here, So what is the main idea? So we have equation, left and right sides, and we know that F transform, is just technique that changed functions to vectors of its components. Therefore, the idea is take equation and apply the F transform to both sides of these equations, and then transform both sides, from functional form to vector forms. So this is the main idea. However, as I said, we shall justify this approach just saying that it is legible approach, that we are able to do it. Therefore, we introduce the following space where everything works, and this is the so-called direct space of Hilbert, direct sum, of Hilbert spaces. Here you see how it is expressed. Direct sum is here. Again, I will not go into the details. Important here is that the F transform will project the solution function to each component of this space. And then the trick which I just explained is expressed here. And here you see how we apply F transform to three functional parts of our equation. You remember that we have equation which has three functions involved, and then because F transform is again operator form, each function is transformed into vectors. So this form is just the linear matrix form. Matrix will appear later. Linear matrix form that contains unknown vector denoted as the F transform vector of function y. This is F transform of the integral form, and this is again F transform of the known function g. The most tricky part is this one, because if we see, if we look at this equation, and we now have the problem how to solve equation. We know from elementary mathematics that equation is solved using the transformation. Unknowns we shall put on one side and knowns are kept on another side. Yeah. However, here we have unknowns on both sides. Yeah. Y is unknown function, I remember. Yeah. And here it appears, yeah, as F transform, but here, yeah, it is hidden under the integral operator. And therefore the trick is how we can extract the unknown function y from this complicated form. Yeah. And this will be explained a bit later. Yeah. In any case, yeah, the space which I have introduced as a direct sum of Hilbert spaces is useful to confirm that the solution which we find in the form of vector of components, yeah, is a really good solution for this type of problem. And this is the illustration, yeah, how we actually approximate. So this is a new idea of approximation, because we used to somehow imagine that approximation is a smooth function which is close to the given one. Here we have approximation using the F transform components as vectors, yeah, and component each component actually is a piece of constant function. Yeah. So here you see how the constant pieces approximate the function which is represented using this smooth curve. Yeah. This is approximation by vector components. Later I will show you how we can construct this smooth approximation. So after all these explanations, yeah, the basic steps, yeah, are as follows. So take equation, represent it in this form, yeah, then replace this integral part, yeah, by the linear form, and this means that, and this is the most tricky, how integral form, integral operator can be represented in the form using matrix multiplied by vector, using matrix form. Yeah, it is possible, and the trick is just to extract the so-called operational matrix. Yeah, this part will be explained by Tom, and then when we do it, yeah, we will have what we just wanted to have. Yeah, look, so the unknown vector is here. Here, this is again unknown, but this is linear form. This is matrix. Yeah, so we can do elementary transformation, putting everything the left part, for example, and just find the unknown vector multiplying by the inverse matrix. Luckily, the inverse matrix in this case exists. And then when we have, yeah, the solution in the form of inverse of F transform components, we apply the inverse F transform, and we have smooth approximation as we actually want to have. Yeah. So here are details, yeah, technical details, some of which will be presented by Tom. Okay, so please, yeah, you have actually 5 minutes. Yeah, so I didn't give. I'm sorry.
So if we use the uniform partition, then the errors in here is very big. However, in this part, we do not make the not do the not partition, do not need very small. So the errors here is very small. That's why here we use the great fuzzy partition, which gamma is larger than 1. Then this is the chart of the fuzzy partition that we use. See that the distance here is quite small compared to the distance in here. And this is like the arrows here is more. But the arrows here is smoother, smoother. And here is the fuzzy partition. Fuzzy partition of function f would be described by this formula. And this one would be is the inverse fuzzy partition. And now here is how we apply fuzzy transform for the approximate solution of our problem. Here we apply fuzzy transform for both sides of this equation, and we got this formula. Here, let's see that fuzzy. This part is easy to make. This part is so easy as well. However, this term it problem because this is we apply fuzzy transform for this integral operator. So our purpose here is to transform this fuzzy transform into inside, and here we can represent this term by the multiplication of the magic and data with the fuzzy transform of the unknown function, and because which this metric can be estimated by this, which the element could be computed like this, and you can see that the norm between the distance of this term and the multiplication is quite small. And now, by our estimation from this formula, we got this magic equation, which the unknown y is so easy to determine. And here, after we determine the vector y, then we apply fuzzy transform to get the approximate solution. And now this is the example that we consider. And this is this is our result. And in here you can see that we compare with the result of this paper, that our result is quite better than this result. And you can see that from here, gamma equal to 1, we have uniform partition. And this is a graded partition. And you can see that in here, the result here is much better compared to this result. And once more with n equal to 20, and you can see that the result is similar to the previous when n is 10. This one this one is much better than this one, and this is for the blue line. This is the expect solution, and the red bar is our approximate solution. And you can see that this is almost the constant. And let's choose the end of.
Okay, thank you. So time for 1-2 short questions here, because as I said, so we just spent the time requested, and we can extend it. Yeah. Are there some questions? No questions. Great. Very good. Yeah. So I only wanted to stress, regarding this presentation, that really the quality is good, because, as you said, the n parameter n, which Tom showed you in two last slides, refers to partition elements actually. So with 10 or 20 partition elements, which is nothing for approximation methods. So we obtain really nice results in the approximation quality. Okay, so I will not use our time anymore. So once again, thank you for your attention. And now my role is to chair the session. The second talk, as I announced, will be online. So the speaker, I see the speaker, is.
Good afternoon to all. You hear me?
So as you see, the title, and so I will not read, you will do it, just introduce yourself, and you can start your presentation.
Oh, thank you. I am Anarita Samushi, and I thank you to you and to all to give me the opportunity to speak in this conference. The subject of this talk is in the field of integral inequality in an additive setting, which have application, for instance, in statistics, in computer science, in decision theory, and image processing. Moreover, in real application, some situations arise that motivates the introduction of set-valued analysis, and for this reason, we have extended our results to the multivalued case. Wait. Okay, this is a list of potential fields of application of the framework we proposed. In this slide, I have put some papers related to the Birkhoff-Wick integrability that we have obtained. In this talk, I will mainly focus on the results contained in the last two papers, with particular attention to inequalities. The notion of integrability we consider is related to the partition of the whole space T. So we take in this partition a relation, or the relation, which is that given by II, and we say that a partition P prime is finer than a partition P if P prime is a refinement of P. And for what concerns a property that holds almost everywhere, we use this one. Okay, on the family of partitions, we consider in particular the tagged partition, and the definition of the integral we consider is the following. A scalar function u is a Birkhoff-Wick integrable if there exists an element of R, we call here B, such that for every epsilon greater than 0, we can have a pair. A pair, a partition P and an integer n, such that for every finer tagged partition and for every n greater than n of epsilon, the Cauchy-Riemann sums are close in this sense to the element B. The Birkhoff-Wick integrability on every measurable set is defined in the usual way, and we obtain the following results. Let me go back for a moment. An integral of this type was introduced in Banach spaces for countable additive measure by cadets and selling in 2000. And they use instead of Cauchy-Riemann sums here unconditionally convergent series. And if we are in the case of countably additive case with sigma finite measures, the Birkhoff integrability by cadet-Stellin and the integrability in the weak sense we introduce here are equivalent. Now, the family of all Birkhoff-weak integrable function is closed with respect to the order of the real line. If a function is bounded and equal to 0 almost everywhere, then it is integrable and its integral is 0. Moreover, if the space T is countable, to each scalar function we can associate this series. If the series is unconditionally convergent, then the function u is integrable and its integral is exactly the sum of the unconditionally convergent series. Okay. The Birkhoff-weak integral is linear and is absolutely continuous with respect to Ni if the function U is bounded. Moreover, if we take p greater than 0, and we consider a scalar function u such that its p power is Birkhoff-weak integrable, we can associate to each u this p root of the integral of the p power, this functional. Usually this functional satisfies the triangle inequality for p greater than 1, and so this will be a semi-norm. Instead, here we consider also the case that p belongs from 0 to 1. In this case, the triangular inequality is not satisfied, so this space is not normed. In any case, we consider conjugate indices also when p belongs to 0 from 1, and in this case, q must be negative. Okay. Now, in order to address the Minkowski and Holder inequalities, as well as the reverse inequalities, we consider set functions that are integrable in the following sense, namely the characteristic function on every measurable set is Birkhoff-weak integrable. Obviously, all finite measures are integrable. Here we give two examples. One, the first, I call it example A, with a set function which is only a continuous from below subadditive, and thanks to the geometric series, it is also integrable in our sense. In the second example, instead, we construct a set function which is again continuous from below, again subadditive, but not integrable because of is constructed using the harmonic series. From now on, we consider the set function we consider are integrable, continuous from below, and subadditive. Okay. For our results, we consider also measurable function. Even if for scalar Gauge integral such as Enstock, McShane, and Birkhoff, no measurability condition is required a priori, but we need for our result. In this setting, okay, in this setting, when p is greater than 1, the Holder inequality holds for conjugate indices and for measurable function whose p and q powers are Birkhoff-weak integrable, while for the Minkowski inequality, this is true for p greater or equal to 1 if these function considered and their powers are, by assumption, Birkhoff-Wick integrable. Now, when P belongs to 0 and 1, this is not true, is no longer true in general. For example, if we consider the set function defined in example A, we show that the Minkowski inequality fails to be true. And so this functional is not a norm and the corresponding vector space is not normed. The failure of the Minkowski inequality is a consequence of the fact that when P belongs from 0 to 1, the maps that send T to its power is concave, and what we are able to prove is that the Minkowski inequality reverts its direction under suitable assumptions. Therefore, the usual subadditivity fails and is replaced by superadditive. The main results we obtain is the inequalities can be reversed under suitable assumption. The assumptions are comparable with that introduced in the previous case, P greater than 1, with this additional condition assumption on the V to the power Q. So we obtain the reverse order inequalities and also the Minkowski reversed inequalities. In particular, the reverse order inequality follows from a kind of Young reverse inequality, this one, and the Minkowski one follows from the older reverse inequalities. As a corollary, we obtain two other following inequalities. This is the first one. I wrote here only for the case P greater than 1, but we can reverse this inequality when P belongs to 0 and 1. And this is the second group of inequalities divided by the value of P. Finally, for P, only for P greater than 1, and when the ratios U and V are bounded, we obtain sharper estimates of the integral of the product and the product of the integral in such a way. I came back a moment. As I said before, the functions for us are measurable. The measurability is necessary in this part, which is not proved, but in order to be sure if that the integral is 0 and u is non-negative, then the function u is equal to 0 almost everywhere. Okay. Now, let me turn to the interval analysis, which is an important field with many applications. We consider the family of closed bounded intervals of the half line and endowed with the Minkowski addition, the multiplication by scalar, and the Hausdorff distance. And we consider also the weak order interval, which is well known in interval analysis, and the multiplication by interval in such a way. So, interval valid functions are defined through their endpoints functions u minus and u plus, and the Birkhoff-Wick integrability of an interval valued functions is defined in an analogous way as in the scalar to scalar case. The only difference is here because we substitute the Riemann sums with the Minkowski addition, and the convergence is understood in the sense of Hausdorff distance. In this framework, the Minkowski sum associated with the target partition can be viewed as an interval whose endpoints are the Cauchy-Riemann sums associated with the endpoints function of capital F. And the Birkhoff integral is of an interval value function F is an interval whose endpoints are the integrals of the endpoints u minus and u plus. The integral is linear in the sense of Minkowski addition. The p power of a Minkowski sum is the interval determined by the p power of the endpoints function of capital F and capital G. And if consider the p power of F, we can define its value, this value here, namely the p root of the integral of the p power. This is an interval which will be exactly the interval with the analogous functional for the endpoints function u minus and u plus. And since we consider as this value the Hausdorff distance between this element and zero, this coincides exactly with the second element, the right-hand side of this interval. So the Minkowski inequality, sorry,
There is a mistake. Our side. Okay, I don't know what to do.
sorry, the line go down. I come back again. Okay, you will see.
Yes, we see. Yeah, so yeah, please continue.
Excuse me,
Continue, yeah, we see your
are
slide.
you hearing
So,
me?
yeah, you have 3 minutes left.
Hello?
So please, hello. Do you hear me?
Yes, I see. I can hear you.
Yes, we also.
You are able to see now?
Yes, we see your slides.
Okay, sorry.
Please
Sorry
continue.
again. Therefore, the Minkowski inequality and its reverse follows from the scalar to scalar case under suitable assumption applied to the endpoints function of the integral, and the same apply to the order inequality and its reverse using interval multiplication we have defined before. Finally, we also examine the case of integrating a scalar function with respect to an interval valued set function. In this case, we consider interval submeasure, this is the definition. It means it is monotone with respect to the weak order interval and subadditive with respect to the Minkowski addition. And this is equivalent to assuming the same properties to the endpoints N minus and N plus set function. The notion of integrability is exactly the same as in the previous case. The only difference is that in the Minkowski addition, now U is scalar and capital M is interval valued. As before, the integral of a scalar function is an interval determined by the integrals of u with respect to the endpoints and function n minus and n plus. The linearity follows from the scalar case, since we have this relation, and the Minkowski and reverse Minkowski equality so are obtained directly from the scalar to scalar case. For the reverse order, we have only to observe that if we have the product of two functions u and v integrable with respect to capital M, this is exactly this interval, and in order to have the distance between this element and zero, we have to take only the right hand side, the right endpoint of this interval. So reverse order and order inequalities immediately follows from the scalar to scalar case when we consider n equal to n plus, and we apply the results of the scalar case. I conclude with this final slide by mentioning some possible future developments. In particular, we are interested in applying to image reconstruction the scalar to scalar case. In this context, we aim to reconstruct a grayscale image using an observed image G corrupted by a noise eta. We consider the minimization of this functional, whose first term measure the discrepancy between the candidate image F and the observed data G, while the second term, when P belongs between 0 and 1, promotes images with few non-zero component, and so preserve, for example, edges. So we want to find a result of this type in order to balance the first addend, which is a sort of regularization, fidelity terms, and the second, which is sparsity terms. And I thank you for your attention, and I say thank you, and sorry for before for the interruption.
So thank you so much. Yeah, fortunately, yeah, you spent even the extended time, and so we can, yeah, effort only one short question, yeah, if any. Probably Mirko, do you have something, yeah, to add? I have only one question, yeah, very short, please, yeah. So you showed that selecting parameters of this type of integrability, yeah, you can reverse famous inequalities, right? Why do you think? Hölder inequality and also Minkowski inequality can be reversed. Yeah. Why do you think that this is an advantage?
I saw some results of this type in additive case with respect to measure, and maybe it is possible to take the noise inside the measure mu, which is non-additive, and so to capture the noise inside this part.
Okay, so thank you. Yeah.
Thank you to you.
This online session, yeah. So yeah, just follow us inside. Okay, so yeah, we are back, and now this is the time for the last talk for today. And this talk, at least was prepared, yeah. So you will begin, yeah. So the title is differential equations with respect to Poisson measures, yeah. So it seems that it can be continued, yeah. I mean, with the previous talk, basic concepts and modeling. And the talk will be given by yeah, Miroslav, yeah? So please, you have 20 minutes, yeah?
I don't know how to use it, uh, so I will just hold it. My name is Milos Lacisko, and I will present you something about differential equations driven by fuzzy measure, which is my work with in collaboration with my supervisor Josef Kyselak. And it's a pleasure to thank the GANs, which is funded here. Okay, so what I'm going to speak about, I will start with some motivation example, like toy example. Then I think it is necessary to start with the basic concept because I think it is not so common. And then we will switch to the modeling and some results of our current work, which will end with some open problems because nothing is done yet. Okay, so uh, we had a lot of toy examples from the motivation. I was deciding which one to choose. So because the modeling is, we are modeling some biological data, I choose this biological model. So let H be the instant level of the immune response at the time. And for the total immune response, we should integrate the instant level. So it is equivalent with some differential equations. Uh, what means if we use Lebesgue measure here? It means that all time intervals have the same impact, and also there are no interaction between the inputs. Mainly in the biological processes, this is not what we want because it's clearly that the more recent uh, what happened in the most recent time should be more significant to the total response, and it should be there should be also some interaction between the inputs because maybe if you take some medicines, the combination of the medicine gives the better result. So we decided to use the fuzzy measure here and the shocked integral. So we have this model. The function h. Yeah. It's just the toy example. Okay, so basic concept. We are working on some omega and some sigma algebra on that omega, which is measurable space, some basic definitions. So set function is any mapping from the sigma to extended non-negative real numbers. Then fuzzy measure, what I think we all know, is the such set function which hold these three conditions. So for the empty set, this is equal to 0. For each set, it is non-negative, and also the monotonicity condition. So this is fuzzy measure. And we know a lot of measures, additive measures, fuzzy measures. And for us, for this presentation, the most important one is the distorted Lebesgue measure, which is fuzzy measure. And how how it is defined, we need that this function m, which is increasing right continuous, and it has zero value at the point 0. And then the distorted Lebesgue measure basically took the Lebesgue measure of some set A, and then the function m is applied on that value. So this is distorted Lebesgue measure. If the m is identity, we have ordinary Lebesgue measure, and in this presentation we are using the power distortion. So let's say that m is function square, or some other powers. Like it is very important to distinguish between when the m is less than 0, less than 1, and bigger than 1, because then there is a concativity or convexivity or dysfunction, and it has different properties. And we are using shocked integral, which is basically just the Riemann improper integral of the survival function. which is defined in the following way. So we are doing the alpha cut, and we are calculating measure of the axis which holds this condition. Yeah, that's it. And how to switch from the integral to the differential equations. So the motivation is in the Radon-Nikodym derivative, which there's the relation between the derivative and the integral. So we want to do something so-called Radon-Nikodym Schocket, or Schock and Radon-Nikodym derivatives, where this integral wouldn't be Lebesgue, but the Schocket. So it is some kind of inverse relation to the Schocket integral. So what is known in this part? Sugeno in 2015 and Nagy and Tora in 2024 dealt with the linear differential equation with respect to distorted Lebesgue measures. And they found out that this equation has solution, which is so-called M exponential function. They proved only that the solution exists. They didn't show that it's unique for some initial conditions. So we wanted to extend this topic. Yeah, the M exponential functions could be basically anything because it is the solution for the particular distortion M. If the M is identity again, then the result is exponential function. Okay, what we did in my rigorous thesis was that we proved that the existence and uniqueness of the solution, if we took the differential equation in normal way with respect to general fuzzy measures. So we extended from the just distorted Lebesgue measures under some conditions, and also it is clear already that the differential equation with respect to distorted Lebesgue measure is the solutions are also there exist and they are unique. And we move it even more. So we proved it also for the system of differential equations. Those conditions for the distorted Lebesgue measures are not so strict that for the general fuzzy measures, because distorted Lebesgue measure has some good properties. Okay, so let's switch to the modeling phase. In the beginning we had the data of the life cycle of some bacteria in the environments with different pH from 4.5 to 9.5. And we wanted to take the model, which was generalized logistic differential equations, or so-called Richards differential equations. We wrote it in the integral form because we wanted to model, to estimate the parameters alpha and nu of this model, so we could feed the real data in the best way possible. Why this model? Because it is usually used in the biological processes. Yeah, and y is just the initial condition, and those are the parameters of the model. And k is usually the maximum value of the measurement y. So this thing in this bracket is less or equal than 1. So this whole bracket is non-negative. So the integrand is non-negative. So the y is a non-decreasing function, which is optimal for this type of processes. And the non-additive model, we just switch the Lebesgue measure to distorted Lebesgue measure. So we have one more parameter because we are dealing with power distortion. So m would be just the Lebesgue measure to the power m. So and one another parameter. So we have three parameters: alpha, ni, and m, which we want to estimate. We did our model in Python, which is good for the data analysis. So how our algorithm looked like, we have table of measurements for each pH. We had 96 measurements, and we started with calculating the Schocket integrals of this thing. So these Schocket integrals plus the initial conditions, and we wanted to have for each t these Schocket integrals, because we want to build the function y for each time. So t0, t1, t0, t2, and so on. We did it for each measurement to get the metrics of so-called, we didn't know how to call it, so we called it in just because work is in progress still, so we called it the cumulative shocked integrals. And then we did the estimation. We used the least square method and the BFGS algorithm, which is just Python NumPy algorithm for the estimation. And we estimated the parameters alpha, ni, and the parameter m of distorted Lebesgue measure. And then in the end, we just plotted the graphs of real measurements so we could compare if our model works well. And so the output was those three parameters and the graphs. So what it looked like. This whole line are the real data for each measurement, and this dotted line is our model. So these three, the red one, the black one, and the green one, this should look like, because the bacteria we can imagine it as the bathtub, but I don't know how to say it. It should start growing exponentially. Then the growth should be less or almost constant, and then it should slowly start dying here. So our model was in this phase almost exactly like the real data. Only thing we couldn't describe, or we don't know why it happens, is this jump in the very beginning. We don't know if it is because of the initial condition. We don't know, but if I cut the graph like here in the 5th second, you couldn't see anything. And those parts are not important. The most important are if we could catch the exponential growth and where this exponential growth stops. Because it is switch from the phase 1, this exponential growth, to the phase 2, which is so-called maintenance part of this life cycle. And this blue one, started the questions why it behaves differently from the others. We think that it is because of some noise, because it is measured in real time, so there could be some noise. So our question is if we could use some noise cancellation in pre-processing to get the better results. Sorry? These are different measurements because we have 96 measurements. Yeah, data are also different. And just to compare it with the distorted Lebesgue measure, as I said, this is m is 0.064, and here we fixed the m to 1, so we have this standard Lebesgue measure. We could see that those graphs are not so good as ours. Okay, some conclusions. Following the theoretical part of the differential equations, we use this concept on a real model. The basic motivation was during the defending of my rigorous thesis, my opponent said that he wants to see some real data or some application if it is not just the theoretical concept. So we use the generalized logistic model because it is used in the similar problems. And instead of additive measure, we used distorted Lebesgue measures. The results were not just on the first side better, but also if I calculated the mean square error for our non-additive model, it was 10 times lower. So we were 10 times closer to the real data. And we showed, so I think that we showed that this concept is not just pure theoretical, but also it could be applicable. And the second motivations, it is not written here, was my supervisor told me that those models are usually used for modeling the fractional differential equations, but they are hard to computation. And this model is very easy, I think, for the understanding. So what is open now? We want to further analyze the discretization of the continuous Lebesgue shock integral because it is what we are doing here. So some Riemann-like approach in partitions of the interval, because we took the continuous integral and we want to write it in Python. So we need some kind of discretization. And we used only distorted Lebesgue measure with power distortions. What could happen if we use general fuzzy measures or another distortions, and how could that be implemented in Python? And maybe for the informatics, how fast was the estimation of the parameters of the model? Because when we are doing some approximation or some numerical analysis, that is a common question, how fast it was. And let's say some experimental questions. could we achieve better results in estimation if we use more statistical approaches? So we took all measurements and we estimated those parameters for all measurements at once. And maybe we can use it like they took each measurement separately, calculate those parameters, and then maybe look at the mean of all those values. So could be better, maybe. And and last question, as I said before, could we achieve better results if we did in pre-processing some noise cancellation? Because if we are measuring something, there is usually some noise. So thank you for your attention.
Data, yeah, and you apply your machinery, yeah. However, your machinery depends on several parameters.
Yeah.
And how you select these parameters, because without them, you could not really obtain a good approximation. And this is rather tricky
Here?
to me, yeah, because I see you have alpha, Ni, and other, and also and also this distortion, yeah.
Yep.
Is parametrical, yeah. So how everything, yeah, can be selected, yeah, in order to have this nice approximation.
We know from the theoretical part that alpha needs to be non-negative or positive even. And we choose the distorted Lebesgue measure with power distortion because it could be easily programmed in the Python. And then the exact values were calculated by the Python by the least square method and the PFGS algorithm. So there was just estimation of the parameters. We knew only that it needs to be positive, and that's it. We started the program and the equation. Okay.
Yeah.
Yeah, we have this one. Yeah. Yeah, we want to find the curve which.
You shall make approximation curve.
Yeah, approximation curve. So we need the parameter of the model. Kind, yeah. Yes, in form of that model, that Richard's differential equation, because it is used in such problems. Thank you.
Thank you.